So welcome to part 4 of lecture 13. In this part, we're going to be looking at operators, and we'll see operators kind of reappear, and we're going to study them more deeply when we get to chapters 6 and 7 of the textbook. Now, what is an operator? Well, a linear map from V to itself is called an operator. Okay, so basically an operator is just a linear map from V to V. Okay, so we need that both the where you're starting from and where you're going to are the same vector space. And because we don't want to always be writing LVV, we sometimes just write LV for the set of all operators. Okay. So one thing that we want to talk about for the rest of this lecture is what can we say about some of the properties of operators. And one of the properties that we have is that when you're checking whether an operator is invertible, you only have to check whether it's injective or surjective. Okay, so suppose that V is a finite dimensional and T is an operator, so it's a linear map from V to itself, then the following are equivalent. T is invertible, T is injective, and T is surjective. Now, normally to check whether something's invertible, you have to check whether that it's both injective and surjective. But what this theorem is telling you is that for operators, it's enough to just check one of those two. Now, let me go through the proof. And so I'm going to show that A implies B, B implies C, and then C implies A. And so I'm showing that they're all equivalent. Now, A imply B is kind of the easy, right? Because T invertible, because it's a linear map, it implies that T is injective. Because invertible implies injective, and it actually means implies that it's surjective as well. So we might as well put that in there as well, even though we don't really need it, because we just wanted to prove the injective property. Okay, so now we want to do is show that if we have an operator, and if T is injective, then the map is also surjective. So since T is injective, we know that the dimension of the null space of T is 0. Okay, this is one of the criterion for being injective. So if we use the fundamental theorem of linear maps, we know that the dimension of V is equal to 0 plus the dimension of the range of T. And so what we have is, since the range of T is also inside of V because we're having an operator, and we know that the dimension of V is equal to the dimension of the range of T, this actually forces V to be the range of T. But remember what this means. If V is equal to the range of T, what we have is that T is surjective, because that's the definition of being surjective, that its range is equal to where you're mapping to. Okay, so there we go. That proves B implies C. And what about C implying A? Well, we already have that it's surjective. To prove that it's invertible, we have to show that the map is also injective. Okay, so we're given that T is surjective, so we're given that the range of T is equal to V. So remember, the fundamental theorem of linear maps comes in again. We know that the dimension of the null space of T, there's two n's in null space, is equal to the dimension of V minus the dimension of the range of T, but this is equal to the dimension of V, and range T is equal to V, so this is equal to the dimension of V, which is 0. Okay? So the null space of T has to be only the 0 element, so T is injective. So T injective and surjective implies T invertible, where we're using a result from the previous lecture. Okay, so there we go. So when we have an operator, it's very easy to or easier to check whether your map is invertible or not. Okay. And kind of as a final fact here that I want to point out is when we look at this theorem here, we had the hypothesis that it's finite dimensional. And I just want to point out that you actually require the hypotheses of finite dimensional because V could be an infinite dimensional space. Okay, so here's an example of we're looking at all the polynomials of any degree, and we're looking at an operator, and I've written it as x cubed. And what I mean by that is take any polynomial and map it to x cubed times p. So we're basically taking a polynomial and multiplying it by x cubed. This is an injective map, but it's not surjective, right? And it's not surjective since nothing maps to 1, for example. Everything on the right-hand side will have degree 3 or higher. Here's another example of where we're going to have something that's surjective, but not injective. So if we take the map S in the set of all linear maps from F infinity to F infinity given by this truncation and shift, right? So we take a infinite series, A1, A2, A3, we chop off the A1 and we shift everything to the left. So it then becomes A2, A3, A4. Okay, this map, this is surjective because I can hit every possible sequence with this, but not injective since we have that 0, 0, 0 and 1, 0, 0 both in the null space of S, so it can't be injective. So just because you're one doesn't mean that you're the other. And that's kind of what this theorem also tells us, right? That the minute you're injective, you're automatically surjective, provided that you're finite dimensional. But it doesn't hold for an infinite dimensional vector space. So just to kind of wrap up for lecture 13 and the end of chapter 3 here, there's kind of a bunch of important ideas. One of the important ideas for today's lecture is the idea that we can think of linear maps as matrix multiplication. So we can take vectors, turn them into matrices, we can take our linear maps, turn them into matrices, and we can think of linear maps in terms of the matrix multiplication. So we're really getting ourselves back to the land of linear algebra, first year linear algebra. We're also going to start seeing our first, we saw our first introduction to operators. And so operators will correspond to square matrices, something that we saw a lot of when you're in your first year linear algebra course. And the one thing that we proved about operators is when exactly an operator is invertible. So there's a bunch of important things here from chapter 3. And that's all I had to say today. So I will see you at lecture 14. Have a great day. Bye.